Section 7.3 talks about existence and uniqueness proofs. And we're also going to talk a little bit more in general about proving for all statements. So the big question we want to think about here is, how do we prove a statement of the form there exists an x such that R of x? And the answer is that we just find that x, if possible. And then we'll see in section 7.4 that it is also possible to prove these when we don't actually find the x. But generally, we're just going to say, okay, I'm trying to show there exists an x, so I give a formula or an expression or some sort of description of x, and then I show that it satisfies that R of x statement. So let's go ahead and look at a couple examples of that. The first statement we have here is that there exists an even prime integer. True, 2 is prime and 2 is even. So my proof would just be consider 2. It's even and prime. Thus, there exists an even prime. So I just found some number that satisfied my R of x, that satisfied my conclusion. And I said, look, I just needed to show it exists. Here it is, therefore it exists. The second example we have here is that there exists an integer that can be expressed as the sum of two perfect cubes, two different ways. So all I need to do to prove this is to actually find that number. That's certainly going to be one that's a lot harder to do, but if I want to just provide a proof, as long as I know what that number is, then I can just say, okay, consider the number. I'll just tell you it's 1729. I'll show you that it can be written as two cubes, right? Perfect cubes are just integers that are cubed, just like perfect squares are numbers that are squared. So I say, okay, if I cube 12 and I cube 1, add that together, that gives me 1729. 9 cubed plus 10 cubed also gives me 1729. So that number can be written as the sum of two perfect cubes, two different ways. So then I'm done. Right, you could put in a concluding sentence there. Look, it can be written, but it's sort of clear from what we have. Now, the only reason where I'm just able to give a example here is because the statement is of that form there exists. If I was trying to prove an if-then, some sort of conditional statement, I'm trying to prove a for all, you can't just give an example. But to prove that there exists, you can. All right, so here's a question for you guys to think about. I want you to show that there exists some natural number n for which 11 divides 2 to the n minus 1. So see if you can figure out which n that is. Now, these existence proofs aren't always so easy, and sometimes there can be an existence proof tied into another proof. So here I have the statement, if a and b are natural numbers, then, so it's a conditional, but after that conditional I have that there exists. So then there exists integers k and l, for which the GCD of a and b can be written as a times k plus b times l. So before we go in and prove that, let's think about what it means. So it says if I have two numbers, a and b, if I find their GCD, so I know for 6 and 4, the GCD, the greatest common divisor, is 2. That should be able to be written as some number times a, well, let me write it in the other order, a times something plus b times something. So I notice if I do a times 1 and b times -1, then I get that too. And right, no matter what numbers I take, if I find their GCD, so the GCD of 12 and 27, that greatest common divisor is 3. That can also be written as 12 times something plus 27 times something. You'll have to think a little bit about how to do that combination. But if I do 27 minus 24, which is 2 times 12, that will give me that 3. So the statement is saying that we can always write the GCD as a linear combination. So that's what happens when you take constants times these constants, as a linear combination of those two numbers. Now these examples are just that. They're just examples to kind of give us a feel for what this statement is saying. So now let's go ahead and do this proof. This is a very complicated proof here. So what I want you to get out of this explanation is sort of just a feel for how these proofs work. This isn't something that you would be asked to produce from scratch on your own. Okay, so I'm proving an if then. So I'm going to start by assuming my if. So I'll say suppose A and B are in N. And now I need to show my then. So I need to show there exists some integers k and l for which the GCD of A and B equals AK plus BL. So we're going to consider this weird set here. So I'm going to consider the set A, which is equal to AX plus BY. So it's all of those different linear combinations of A and B, where X and Y come from Z. So let's actually think about what this is looking like. I'll use my example here where A was 6 and B was 4. And so I can take any number X times that A. So I can do 6 times 1, 6 times 2, 6 times -3. And then I'm going to take B, that's my 4, times any number Y. So maybe I'll do 4 times 1, maybe I'll do another 4 times 1, I'll do a 4 times -1, do another 6 times 1 over here and a 4 times 2. And then I'm going to add all those together. So I get 10, this is 12 and 4 is 16, this is -18, -4, so -22. This is 6 and 8, 6 and 8 is 14. Right, so I'm just going to get this combination of all of these numbers. We saw we could have done 6 times 1 and 4 times -1, and that would give us 2. So 2 will also be in here. I'm also allowed to use 0. So I certainly will have 0 in my set, and so forth. So I'm going to consider this set. It's going to have positive numbers, negative numbers, and it's always going to have 0. So let's write that out. This set has positives, integers, negative integers, and 0. And if we start playing around with this, then we should notice that the smallest number in this set that's positive is actually the GCD. So I am going to let D, I don't know it's the GCD yet, I have to prove that, but let's let D be the smallest positive number. Now I can't have arbitrarily small positive numbers because my positive numbers end at 0. So I know there is going to be some smallest positive number. And I'm just going to call that smallest positive number D. And now, because D is in my set, we know that D has to equal some AX plus BY, where X and Y are in Z, because every number in the set looks like that. So now we will show that D is actually the greatest common divisor of A and B. Because since I've already shown that D can be written as AX plus BY, if I can show that it's also the GCD, then the GCD can be written as A times an integer plus B times an integer, which is what I wanted to show. Okay, so how do I show something is the greatest common divisor? Well, first I need to show that it's a divisor. So I need to show, we'll sort of do a little scratch work over here. I need to show that that D divides A, that it's a divisor of A, and D divides B, and it's the greatest number that divides each of those. It's the greatest of those divisors. So let's first show that D divides A. So to show that D divides A, I'm going to write my A as some number times D plus R, using that division algorithm that we've talked about previously, where this R is going to be some number. The remainder can be 0, or it can be any number up to D, but not including D. Now, if we go from there, we're trying to show that this R has to be 0, so that A really is some multiple of D. So let's solve for that R. So R is equal to A minus Q times D. I know D is equal to A times X plus B times Y. So I have that minus there. So if I just distribute this out and factor out my A, I've got 1 minus QX plus B times negative QY. But now I notice that this R, this remainder, this positive number here, can be written as A times some stuff plus B times some stuff. So that R is in my set A, because that set A contains everything that could be written as A times some stuff plus B times some stuff. But since R is either positive and less than D, or 0, so since R is in A, and R has to be strictly less than D, I know that D is the smallest positive number. So it can't be a positive number, therefore R has to be 0. And that tells me that A is just Q times D. And then if I do the B case, this is going to be similar. So we get that D divides B as well. Okay, so far I was able to show that there is some smallest number D. That D is a divisor of A, and then similarly it's going to be a divisor of B. And now I just need to show that it's the greatest common divisor. So we're almost there. So next, we just want to show D is the greatest common divisor. Okay. So let's consider what we know about the greatest common divisor. So the greatest common divisor, I'm not sure what it is yet. I don't know that it's D. It divides A, which means that A can be written as that greatest common divisor times some m integer. And the same thing for B. It's that greatest common divisor times some n integer, where m and n are integers. So give us some more space here. And then what do we get from there? Well, I know that my D is equal to A times X plus B times Y. So that's the GCD of a and b times m times x plus the GCD of a and b times n times y, which tells me that the GCD of a and b divides d. So it's going to be smaller than or equal to d because they're both positive quantities. But now I know that d is a common divisor. And this is the greatest common divisor. So it doesn't make sense that I have a common divisor which is bigger than the greatest common divisor. So it can't be bigger than. Therefore, we get that the GCD of a and b must equal d. And then I know that that d was equal to some ax plus by because it was in my set A, and that's what I wanted to show. All right, so let me zoom out here. This is quite the proof. And again, I wanted you to just kind of look through this and see if you can kind of follow each step, just to see what an existence proof might look like. This proof is also in the book, so I encourage you, after you take some time to watch the video, also make sure you go back and read the book and just really see sort of how this proof works and see what things you can learn from it. And we'll talk about that a little bit more in class. The other sort of extension of existence proofs we might see are these proofs called existence and uniqueness. So here, not only am I showing that something exists, I'm also showing it's the only such thing of that form that exists. Right? So we'll see these types of proofs a lot in courses like differential equations. So we'll say there exists a unique function f of x such that the derivative is 3x squared and f of 1 is 2. So this is very much like something you would see in 2410 or 3410, a differential equations course. So let's go ahead and actually think about how this works and how we can prove this. So when we're proving an existence uniqueness, we're going to start off with the existence part. So again, I wanted to show that there is a function whose derivative is 3x squared and where f of 1 is equal to 2. So I know if f prime of x is equal to 3x squared, we'll do a little background work here. Taking that antiderivative, f of x is equal to x cubed plus some constant. If I want f of 1 to equal 2, well, this is 1 plus c, so I better have c equals to 1. So then I can just have my f of x equal to x cubed plus 1. Okay, so for the existence part, we can say to see such an f of x exists, let f of x equal x cubed plus 1, then f prime of x is equal to 3x squared, and f of 1 is equal to 1 cubed plus 1, which is 2, as needed. Okay, so I know that there does exist a function whose derivative is 3x squared, and f of 1 is 2. So now I need to show that this is unique. In general, to show something is unique, what we're going to do is do something like a proof by contradiction. So we'll assume there's 2 and show those 2 must be equal. So it's not quite a contradiction. If I assumed that there was 2 that were different and then I showed they must be equal, that would be a contradiction. But here I'm just going to assume there's 2 of them and show if there's 2, those 2 must be equal. So really there is only 1. So I know that there's 1 here. I've got this f of x. That works. So let's assume there is some, I'm going to call it f2 of x, with that new guy, derivative, is also equal to 3x squared, and f2 of 1 equals 2. So assume there's some other function that satisfies these same conditions, and now we want to show that those functions must be equal to each other. So I gave us a little lemma here that we can use. That comes from a differential equations course. You maybe see it in a calculus course. If the derivative of a function is constantly 0, then that function must be constant. Right? So if the slope is 0, then the function is constant. That's all this is saying. So hopefully we can agree with that. And we're actually going to use that to see that this uniqueness holds. So how does that work? Whenever I'm trying to show two things are equal, we often show that their difference is 0. So I'm going to consider my f of x that I have up above and subtract away f2 of x. If I can show that this is 0, then I know that my two functions must be equal to each other. So I'm going to take that, well, let's just consider it first, and then we'll take the derivative. So I get f prime of x minus f2 prime of x. I know that derivatives can distribute across subtraction. So we get the derivative of f of x minus f2 of x is equal to f prime of x minus f2 prime of x. But f prime of x was 3x squared. But that was also what f2 prime of x was equal to, because we assumed they both satisfied that condition. So their derivative difference, the derivative of the difference is 0. By our lemma, if the derivative of something is 0, it's equal to a constant. So that tells us that this difference equals a constant. All right, so from here, this isn't really part of the proof, but this is where we show that if two functions have the same derivative, then they differ by a constant. And that's sort of where this plus c comes in when we do that antiderivative. But let's go ahead and, for this case, we want to actually show that these two things are equal. So that constant should equal 0. So I'm going to then say, consider the case where x equals 1, f of 1 minus f2 of 1, so it still equals c, since it's a constant, it doesn't depend on x. But f of 1 by construction is just 2. f2 of 1 is also 2, so that gives me c. Therefore, my c equals 0. So f2 minus, or f of x minus f2 of x is 0, which tells me that they must be equal. So we get that uniqueness. So we get our existence and our uniqueness there. Now we've talked more about proving things of the form for all x, and usually it's for all x in some set S. And this is a lot like proving an if-then, right? Because I can rewrite this as if x is an S, then p of x. And so what do, right? I just assume x is some element of that x. Now I can sort of do this as well if I'm not even thinking about it in terms of a conditional. Whenever I want to show something of the form for all x, p of x, I'm just going to start with some element x. Maybe it's in some set, and it's going to be fixed but arbitrary. So what that means is that it has to be arbitrary. You can't pick a specific member of that set. But it's also not allowed to change and be whatever value it wants. So I set some value represented by a variable so that it's arbitrary, and then I use that throughout my proof. So let's go ahead and look at some examples of that. Okay, so the first one we want to look at is every multiple of 4 is even. So we'll say every x in the set of, I'll just call it M4, multiples of 4, x is in M2, multiples of 2, right? So that's the type of statement that I want to show here. So what I do to prove this is I'm going to start out with my x satisfying this. So let x be a multiple of 4. Then by definition, x is equal to 4m, where m is in z. So x is equal to 2 times 2m, where 2m is in z. Thus, x is even. Right? This feels a lot like a direct proof because this statement is logically equivalent to saying if some x is a multiple of 4, then x is even. And that's the way we think about proving it. But let's compare this to the second statement. So for this second statement, I've got both a for all and a there exists. So in this statement, it's going to be helpful to sort of think about this proof in that basic way, where we're sort of building up from our quantifiers. So I have for every x in n, so to start that proof, I'm going to let x be just a fixed but arbitrary element in n. So it can represent any element of n at the same time, but it's not allowed to change once we set it. But you're also not allowed to think of any specific number, right? So it's kind of weird here. And now I'm doing an existence proof with my y. So I need to say what y can be equal to, because for an existence proof, we want to say what it should be equal to. So let y equal something. And I want x times y to equal 4. Well, here, because this x was fixed at this stage, I am allowed to use it in my definition of y. So I can just solve for what y should be, and it is allowed to depend on that x because that came before it. So let x be an n, let y equal 4 over x, then x times y, that's what I want to say something about, is equal to x times 4 over x, which is equal to 4, as needed. So that is sort of how we can go about doing these proofs, where I have these nested quantifiers, where I have a for every and then I have a there exists. So the for every, I let it be fixed but arbitrary. For the there exists, I say what it should be equal to, but I'm allowed to have it depend on anything that comes before it, and then I just show that it satisfies that condition. So I want you to do a proof of the similar flavor of the one we just did. So I want you to prove that for every x, there exists a y such that x plus y is less than 0. So go ahead and see if you can come up with that proof, and we'll talk about that in class. So then section 7.4 is pretty short. I encourage you to read through that in the book, but it talks about the difference between constructive and non-constructive proofs. So far when we've talked about these existence proofs, we're able to construct the thing that we know exists, right? So when we said there exists an even prime number, we were able to construct it. So we were able to lay down exactly what that was equal to. There's also some existence proofs which are non-constructive, where you can show something exists without ever actually referring to it or writing it down or describing what it is. So that's called a non-constructive proof. So this next proof is somewhat of an example of a non-constructive proof, and I really like it. It's one of my favorite proofs. So let's go ahead and see how this actually works. I want to show that there exists irrational numbers x and y for which x to the y is rational. So let's start off here. So let's let x equal square root of 2 to square root of 2. And y equals square root of 2. So we know, we've saw before, that square root of 2 is irrational. So I know that y is irrational, but we don't know about x. So this isn't going to be a constructive proof because I don't know for sure if x is rational or irrational. So case 1, if x is irrational, then x to the y is equal to root 2 to the root 2 to the root 2. I know that when I take a power to a power, I multiply the exponents. So I get root 2 to the 2, which is just equal to 2. So we have x is irrational by assumption, and y is irrational because it's the square root of 2, and x to the y is rational, as we just showed. But we don't actually know whether or not that case is true, so we have to consider the other complement case, where if x is rational. So if x is rational, well then x equals root 2 to the root 2, which is of the form irrational to the irrational power, because I know square root of 2 is irrational. Thus, there is some number of the form, we'll use different letters here, a to the b, where a and b are irrational, but a to the b is rational. Right, so I don't actually know, I didn't actually construct a specific example. I constructed one of two examples. Either this is irrational to the irrational, or this is irrational to the irrational, and one of them gives me rational. I'm just not sure what one. So that's sort of a sort of interesting, tricky example of a non-constructive proof, but it's like still pretty constructive because I have like half of an example. So I encourage you to kind of look through. The book has an example of a constructive proof of this fact if you'd like to compare that. But think through this proof, think about what happens. I think it's pretty neat.